Okay, sound wave interference. So in this problem, there are two speakers, and you are directly in front of one of them, as shown in the diagram there. And we're given the dimensions of everything. I'm going to go ahead and solve this symbolically, and then we'll substitute the numbers in at the end so that you can have a more robust solution to this. So the idea here is that the observer begins to walk directly away from the speaker, just kind of in the direction of the arrow shown there. And the question they're asking is, at what distances from the speaker do you hear a minimum sound intensity? And they give us the temperature so we can look up the speed of sound. So we're after the minimum sound intensity, so we know that we're interested in the destructive case, right? So right away, I want to remind us of that. We care about the destructive case. That tells us that the path length difference is equal to, the way we'll write this is m plus 1/2 lambda. What that's about is that the path length difference is equal to some odd multiple of 1/2 wavelength. When that happens, you'll have destructive interference because the waves will be at completely opposite spots in the cycle. All right, now I'm going to draw like a more geometric kind of diagram of what's going on here. So you've got the two speakers here, and they're in phase, so we don't have to worry about any kind of situation there. We know the distance they are apart. And then I'm going to say the position of the person is over here. It's in front of this other speaker. So these two speakers are distance d apart. Let's solve this symbolically. Here are the speakers doing their thing. And then here is where the observer is, here at point P. So I'm going to call this distance S, and that is what we're trying to find, right? They're asking us at what distances from the speaker do you hear minimum sound intensity? Then I'm going to label this distance here, basically the hypotenuse of the triangle S prime, and it is the hypotenuse, so it'll be equal to S squared plus D squared. I care about this because, of course, I care about the path length difference, right? And the path length difference, if we consider these, let me just label these speakers A and B. The path length for speaker A is equal to S, and the path length for speaker B is equal to S prime. Therefore, the path length difference is going to be equal to S prime minus S. I can write it out that way. I know that S prime is going to be greater than S, right? Because it's the hypotenuse of that triangle there. So I can define my delta R that way. Okay. So my delta R, let's do this over here. If it's equal to S prime minus S, I can write S prime in terms of S, right, as S squared plus D squared minus S. All right, there's my path length difference. I know that I need to take that path length difference and set it equal to my m plus 1/2 lambda. So if I do that, I'll have this root S squared plus D squared minus S is equal to m plus 1/2 lambda. Now at this point, you can go through the algebra to solve for a general expression for S, which is what I did. I tend to like those general expressions. They're the most powerful and useful, I think. Or you can start plugging in different values of M right here and do the algebra repeatedly. I like to, I'd rather do a slightly more complex algebra one time and then be done with it. So that's what I chose to do there. All the algebraic details are in the written solutions, so I'm going to let you look those up there. So algebra intermission right there. And what we end up with is an expression that looks like this for S. Remember, S is what they're asking us for. D squared minus m plus 1/2 squared lambda squared all over 2 quantity m plus 1/2 lambda. The algebra actually isn't that bad. It's maybe 6 lines or something, 5 or 6 lines. So yeah, and then you're able to solve for S. Now, Okay, they ask us, remember in this problem, at what distance is. So what I did is I just made like a little table. This is often useful in these kind of cases, is just to make a little table then and say, all right, well, I know what my different values of m are. What are going to be my resulting values of x, depending on those m values? And you can just go for it. I just chose to do 0, 1, and 2, and then you can go on from there, right? If I plug in 0 plug in my other values to d is given, right? If I plug in 0 for m, I get somewhere around 17.88 meters. If I plug in 1, I get something around 5.62 meters. If I plug in 2, I get 2.98 meters. Oh, actually, no, that's all we can do. We don't want to go any smaller than that because we're told that you start walking from 2.5 meters. So yeah, that's it. It would just be those three cases then.